trouble on the expressway?
No, I didn't get any sleep yesterday, so I kind of stuck down a minute. I was just tired trying to catch up.
Didn't get any sleep yesterday. I thought you slept at night. Sounds like you get your nooner, huh?
Like yesterday, not last night, the night before, I didn't go to sleep till 12, and then we had 6 a.m. workouts.
Oh,
So I got 4 hours of sleep, and then I was up all day until like 10:30 last night. So
yeah.
it's just hard to get out of bed this morning.
Yeah. Well, working on that calculus late, that keeps you up, doesn't it? Yeah, I thought that might be it. Okay. Huh? In physics. Yeah. That's not two easy courses there at all. Okay. Okay, we'll go from current slide. We are recording, by the way. We got all that about your lack of sleep. Okay. Let me remind you, of course, and did you find out? Yeah, you said UAB is still open on Friday, right?
Yeah.
As far as you know. Okay. We are closed, so if you were planning to take care of any business here, don't bother on Friday because college will be closed. The whole both campuses, no one will be on campus. So police, they'll be trying to get you off campus. Okay. So I won't have office hours on Friday. Number 2, I think neither one of you can do math team next year because you'll both be gone. Sad. Okay. Now, and number 3, vote December 12th. Don't forget. Okay. So let's move on to, this is where we left off last time. And I can't get all 3 of these on, so I'll try to get 2. And then we'll do the other 2. All right. This is what we were doing with integrating I don't think the problem was written here. Well, it may have been. Let me move up one then. Nope, sorry. Yeah, okay, sorry. Let me get this on here first. I think I showed this last time, and we talked about it some. If you're integrating an improper integral, in other words, it has an infinity somewhere around it, okay? And we can't integrate to infinity. I mean, that's not a number, okay? This is supposed to be a definite integral, so an improper integral, okay? That's what they call them, right? Yeah, proper integral, okay? So what we do is let's make that some number r, and then let r go to it. But if you let that be a number r, you can integrate this, okay? And the antiderivative of this would be minus e to the minus x, right? Okay? And then if you plug in r, that would be a minus e to the minus r, minus a minus would be a plus e to the 0, which is 1. So it would be 1 minus e to the r. Okay, that's what that integrates to. Well, then take the limit of that as r goes to infinity. As r goes to infinity, e to the minus r is going to 0 really quickly. Okay? So as r gets bigger and bigger and bigger, this gets closer and closer to 0, that gets closer and closer to 1. So that's how we do it. Now, the next figures are going to try to illustrate that concept. E to the minus x. That's what we're going to be such a pain in the neck how you have to do these. Okay. Well, we can't start with 1. Let's get these done. Okay. So here is the integral from 0 to r of e to the minus x. Okay? That's going to be this 1 minus e to the minus r. Okay? That's this area right here. Finite region has an area. Now, if you let r go to infinity, okay, closer and closer to just get larger and larger and larger, after a while you're not adding very much. But this 1 minus e to the r, e to the minus r is a positive number. So this is 1 minus a number, but that is going to be a very small number, okay? Very small number. Very, very small number. So the larger r gets, the closer this thing gets. Okay? So that's what this is showing. The area approaches 1 as r gets further and further out, closer and closer to infinity. Okay? So, the unbounded region, and this really just keeps on trucking, it's so minusculely small, it's not adding very much to it. It actually is trying to get it up to the point where it's 1. Not quite there, ever, but it's getting closer and closer to that. So this is, even though this integral is going to infinity, it is an unbounded region, but it has a bounded area. 1. That's what they're talking about here.
What if that was going to, what if it wasn't negative x?
If that was a positive x, e to the x goes like this, okay? And as x goes to infinity, that's unbounded, period. It explodes, yeah.
That's what I was always, when we did the limits,
Got it.
how 1 to infinity, it was kind of always confused me. That
Right.
I guess infinity is that kind of.
Yeah, right. And even though this is going to infinity and you're always adding a little bit more, you never get up to e to the minus x. And I mean, you never get to 1, but you're getting closer and closer and closer and closer to 1. Okay? Because this thing right here is always less than 1. No matter how big r is, it's just immaterially small, but it's getting closer and closer to 1. Because this thing is going very rapidly towards 0, but never gets to 0. Okay. But if this was not, if that was a plus there, yeah, that's floating. So yeah, it has no limit. Yeah. Good question. Okay. Now, here is the definition that goes along with what we're just saying. Okay? An improper interval, fix a number a and assume that f of x is integrable over some limit a to b, for all b greater than a. Then the improper integral of f of x over a to infinity is defined by the following limit if it exists. And that's the deal, if it exists. The integral from a to infinity of that f of x, assuming f is integral, okay, on any a to b as long as b is greater than a, that would be the, just change the infinity to some number r, do this tells you it's integral, find out what it is, you'll have r somewhere in that answer, okay? If r in that answer is something that is a very large thing, and you keep getting larger and larger, it has no chance of what we call having a limit, we'll just say it that way. But if r is in something that's getting smaller and smaller and smaller, and that over time is going to 0, then this could have a limit. Okay? We say that the improper converges. That's what we're trying to think of. We say that the improper integral converges if this limit exists. Whatever this integrates to, you plug it in. If r is being raised to, if r is an exponent, like 0.1 to the, let's not use that. Let's 1.1 to the rth power, and that's just being added to something. As r gets big, that thing is getting bigger, 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 bigger. Okay.
When you say plug r in, you mean like really plug like a number in, or plug like
Yeah, r represents just some number, any number, and then as you let that number get infinitely large, if the thing there blows up, because you know, 3 to the rth power just keeps getting bigger and bigger and bigger. You know, 3 squared is 9, 3 cubed is 27, 3 fourths is 81. You know, the numbers just keep getting bigger. As far as your exponent there, it's going to diverge. It never, it just keeps getting infinitely large.
So are you saying like plug any number? Like I get that what you said, but if you were going to do that problem,
yeah.
Like go back to the equation here, would you put R in just to kind of represent?
Yeah. That represents a number, some number.
I didn't know if you actually plug a random number in. Or
No, you plug in R, but then you allow R to go toward infinity. Now, if you plug it in something that is condensing really quickly, that probably has a limit. If you plug it in and then something is blowing up, that has a limit. Yeah, that's exactly what you do. You evaluate the result of that integration, antiderivative of x, with R plugged in there, just like you do with the definite integral. See where it falls. Like the last one is minus e to the minus r. As r gets very big, e to the minus r gets extraordinarily close to 0. And so that would have a limit. Okay. But if it was e to the r, like you asked about before, it blows up like crazy. Okay. It converges if that limit exists. R goes to infinity if that limit of the antiderivative with r plugged in there, substituted in there, if that comes out being a finite limit, you know, it does exist, then it converges. It diverges if the limit does not exist. If there is no limit, if it just keeps getting infinitely larger and larger and larger, that limit doesn't exist, so it diverges. So this integral is not calculable. You know, you can't deal with it. Okay. That's why they make such tiny little print on the slides. Okay. Now, what if you had a deal like this? You have 2 infinities, one negative infinity, one positive infinity. You can't evaluate those either way. So what we do, we split this into 2 integrals. From negative infinity to 0, or actually any other number you want to do, 0 is one in the middle kind of it. And then do the second integral from whatever that number was, whether it's 0 or 17 or whatever it was, to infinity. Then you do this one with the r down here, or this one with the r up there, and see if those limits exist. If both of them, the limit of those integrals exist, then you can add them together. But if either one of them blows up, the whole thing's gone. Okay. Make sense? Okay. All right. Now, I'm not testing you on these, but would it be helpful to see an example? Maybe one. Okay. Let's see if they're going to do one here. I think this is it. Yeah. And that's why I don't like to spend a lot of time on them, because, I mean, what do you ever really do that goes to infinity? Practically. I don't know. I mean, maybe there are things that do, but it seems like to me it's just, oh, well, let's do this. This will make it interesting. You know? So, seems like most of the time we're dealing with finite situations. So, this is the, I'll show you the deal here first. Okay, here is your function. F of x is equal to 1 over x cubed. Okay, now if you're integrating that from 2 to infinity, then they say, you shouldn't say it yet, but this is, so let's get out of this and let's actually do it. It says, show that the integral, whoops, all right, show that the integral from 2 to infinity of dx over x cubed converges and compute its value. Okay? Now, If I ask you to do that integral, what's the first thing you're probably going to do with that?
Let u equals x cubed. No.
Okay, I won't. What would you do?
I want to say a log.
That's not. Okay.
Let's put x3 in the denominator.
And what would it become then? That sounds like a capital idea. We'll rewrite this as the integral from 2 to infinity of x to the minus 3 dx. That's the same thing, right? But that's something I can integrate. The other, I guess I could, but I don't want to. I don't want to fiddle around with logs or substitution. That we can do straightforward. That's a power. What would that give you? Well, no, we can't do it to infinity, but what we can do is do it, the limit, as you want to use r or something else. Okay, r. R going to infinity of the integral of 2 to r of x to the minus 3 dx. Now let's do the integral first. We won't worry about the limit for a while here. What is the antiderivative of x to the minus 3? Is it negative 2? Okay. Say it a little slower and louder for me so I can follow it. Okay. Are you saying the exponent or the coefficient? Okay. Let's start with the variable. Okay. That would be x to the minus 2, right? Because you add the 1, right? Now I put the minus sign up there because I knew it was going to be a minus 2. And then what do? It's over the n, right? So that would be over, and the minus is already there, over 2. Wouldn't that be it?
I was thinking, we were doing fractions so much, I don't know, I was thinking.
Yeah. Well, let's take a derivative of this and see if we get that, because a derivative undoes an integration. So that would be a minus 2 times a minus 1/2, right?
Yeah.
X1, yeah. That would be plus 1. X to the minus 3. I think that's right. So the limit of that, but we haven't put our limits on there, evaluated from 2 to r. Okay? So don't worry about the limit yet. Just write it down. R goes to infinity. Okay, of, and what would this be? Negative. And let's move that x squared on downstairs. 1 over 2 times r squared, right? Minus a minus, which would be plus, right? 1 over 2 times 2 squared, which would be, 4, and that would wind up being 8. So let's rearrange that a little bit. The limit, as r approaches infinity, of 1 over 8, that's the plus one, I like leading off with the plus, minus 1 over 2r squared. Okay. Now let's take a limit. And what happens if r gets extraordinarily big, and you square it, that really gets big, and then multiply it by 2 and it's even bigger, so 1 over an enormous number is getting close to 0. So sure enough, that's going to go to 0, so it's going to be 1. Right? we found out number one, it does have a limit, and number two, the limit is 1/8. So we did both of them. Show that it converges. It does because the limit exists. And compute its value, we did that as we were doing. So that is indeed 1/8. Okay? And then that's the shaded region of this. This is the integral of 1 over x cubed, okay, from 2 to infinity. And as you see here, it's always 1/8 minus whatever that value is there, and r. And as r gets further out here, that gets closer and closer to 0, so it gets closer and closer to 1/8. So that limit does exist. All right. Did you want to do another? Are you happy with that? Oh, yeah, we're fired up now, aren't we? Okay. I'll show you the graph of the next one. Okay. This time we're integrating from negative infinity to -1 of dx over x. Okay? Now, the f of x would be 1 over x, so we're writing that as x to the -1. Okay? That's what we're integrating. We're going from negative infinity to -1. What is the antiderivative of 1 over x? Or x to the -1? This is the one I would have left 1 over x. That's the log, natural log of x, right? Okay. Now, Houston, we kind of have a problem here, don't we? You can't take the natural log of any negative number, okay? So,
If you plot it,
what's that?
if you flipped it and change the signs, pretty much the same thing going the opposite way.
I mean, like this. Yeah, well, the deal here, and this is, I think, a really lousy example to do with this. Why didn't we just do from 1 to infinity or from anything else? That's sort of what you're saying. That limit wouldn't exist either, okay? Because then, if we were up there, okay, that would be the log function, okay? Well, if this were 1 over x over here, this would be one like this, right? And that would be log x from 1 to infinity. Well, log has no limit. As r gets larger and larger and larger, so does your thing. So why did they start one that you have negatives that you can't even calculate anyway? Why did they do the other one that you can calculate, but the limit would be infinity? Limit, log of 1 would be 0. Yeah, that's how the log goes. Okay, and log just keeps increasing. It doesn't flatten out. It doesn't have a limit here. It just keeps increasing. It increases really slowly, but it just keeps increasing. There is no limit to log. So therefore, if you had done this one over 1 to infinity, that would have no limit. And certainly, if you did log of x and you try to plug in negative numbers, you can't, because you can't take the log of a negative number. So this one just is out of the question anyway. It looks like a negative area to boot, but this doesn't converge quickly enough. There is always some other value there that you're adding to and adding to and adding to, and you're not reaching any upper limit. The other one was 1 minus or 1/8 minus or something like that. This one's not. It's log x minus 0. Well, log x doesn't converge at all. So therefore, it can't. So I thought this was a pretty lousy example, but it doesn't converge, therefore it's infinite, so it doesn't have a limit. Okay. Now, in case you ever do need these, where in the world is my cursor gone? Why the cursor has disappeared, I don't know, but I got there anyway. All right. If you ever need to do these, here is the p integral from a to infinity. Okay? If you're doing a dx over x to the p, okay, then we've already seen if this p were a 3, that limit exists. If it were a 2, that limit would exist. In fact, anytime p is anything greater than 1, 1.0000001, okay, that would have a limit, okay? But if it's anything less than or even equal to 1, that doesn't have a limit. If it's equal to 1, that's a log doesn't have a limit, okay? But if it's less than 1, then it certainly doesn't have a limit, okay? Because, but, so that's the p rule. And what is the limit? If it does have a limit, this would be x to the minus p. The antiderivative of that would be x to the minus x to the you increase it by 1, so it's a minus p plus 1, so it's 1 minus p. That would be your value down here, and with the r, that would go to infinity, so it's over. They've done some sleight of hand here. Okay. If you actually did this, it would be x to the minus p. Antiderivative of that would be x to the minus p plus 1, right? Over p minus p plus 1, which is 1 minus p, okay? But you have a minus sign there, because that started off being negative, right? So the minus sign will flip the 1 minus p to be a p minus 1, and you don't have a minus sign. So the exponent will be minus p plus 1. The denominator would be minus p plus 1, but you have a minus in front, so that they just flip the denominator and make it p minus 1, and keep that one as 1 minus p. And that's your answer. No matter what your p value is, as long as it's greater than 1, 1.3. So, it doesn't matter. That's going to be your answer. Okay? But if p is less than 1, or even equal to 1, it's never going to converge. It will always diverge. Okay, and that's called the p integral test. All right. Now, here we go. What if we go the other way? This is also an indefinite integral, or infinite, improper integral. But here, the integration is from 0 to 1. And you might think, oh, no problem there. But if this is x to the minus 1/2, 0, that's not defined, right? Because it would be 1 over the square root of 0. No, it's not even defined there. But can you still take an integral there? That's the question, okay? And sure enough, you can by doing the same trick you did before, but this time not from 0 to 1. You do it from r to 1, and then let the limit as r approaches 0. Because it's not defined at x equals 0. but it is defined for any r greater than 0, but then let the limit as r approaches 0. And sure enough, this one would have a limit, and the limit would be 2. You can read through it. I can do that one if you want to see one like this too. Do you? Pretty far up. Okay. You want to see one like this, or the other way? Okay. This is example. Well, I don't know where it is. There it is. It's not quite. Where do they refer to example 5? Okay, there it is. All right. Yeah. Only our book says 9, this one says 1. So.
Example 9?
What's that?
You said example 9?
No, it's not. It's following example 6. That thing that says unbounded function on page 417. Do you have page number on it? You see the thing right before it says definition of unbounded integrands? Okay. Okay, the only difference is it's 9, this is 1. Okay. So there's what the setup is. Let me do it, but I'm going to do it the way it is in the book. The integral from 0 to 9. Now this doesn't look like an improper integral, does it? dx over x, the square root of x. Okay? Now, before you do the problem, how would you like to change it so it's a little handier to do?
Maybe x to the 1/2.
0 to 9, x to the minus 1/2 dx. Okay? And is that integrable? What's that?
Yeah.
Okay, good. How?
The limit. That'll be 1/2
X to the 1/2.
over 2.
No, over 1/2, which is multiplied by 2. Right? Yeah. Evaluated from 0 to 9. Okay? Now, we are getting by with something here, but let's do, what does that give us?
So that'll be 3. So 6.
6 minus 0. So that integral would be 6. Okay? What we're getting away with is the fact that this thing isn't even defined x equals 0. Okay? But it still works, and you can do that. Okay? So we skated by because that was that. Now the one in the book, it had it going to 1, and if that was 1 there, this would be 2 times 1 is 2, and that's why we say that the infinite shaded region has an area of 2. Okay. Oh, let's say, by example 2a. That's not our 2a. Okay. I don't know where the 2a came from. Okay. But anyway, when you have something like this, if you can go on and integrate, do it. You'll probably get an answer. If you do, it's okay. However, you may not get an answer. You shouldn't have gotten one, but it did work out that it was all right that you did. But that does have an area if it's going to 9. Just that if you go out here to 9, you got a lot more area. That would be an area of 6. Okay? Because it's terminal here, and even though it's infinite here, it's an unbounded region. But you're adding so little amount there, that it's bound to be 6. Or if you went only to 1, it would be to 1. It's a 2. Okay. So let's look at the other type of an improper integral, okay? And that would be integrands with infinite discontinuities. And that's what this is talking about. All right. If f is continuous on some semi-closed interval a to b, where b is not included, but a is included, but discontinuous at b, then we can do the integral there, okay, as the, if the function is discontinuous at b, you really can't integrate that. So what we do, we take the limit and let r approach b from the left, from the negative side, and do the integral from 0 to r, and do that. And then do the integration, see what we get, then let r approach b from the minus side. And if b blows up, if whatever that expression is, your antiderivative, blows up as r is getting close to b, the limit doesn't exist. Okay? But if it doesn't blow up, if it converges there, then the limit does exist. Okay? Similarly, if f is continuous on open-ended from a to b, which is what we just did from 0 to 1 or 0 to 9, but it's not defined at 0. If this is continuous at a, then the integral from this, even though this is discontinuous, making it improper here, then take the limit as r approaches a from the right-hand side, from the plus side, and do the integral from r to b f of x. If you can do that one, and then let r approach a, whatever it was, in our case it was 0, no problem. Okay. In both cases, we say the improper integral converges if the limit exists, diverges if it doesn't exist. Okay? So that's the second case of an improper integral. One is if one or the other of the limits is is infinity. Okay, that's improper. If both of them are infinities, one's negative, one positive, split it into 2 and let one go to r, the other go to r. If both of them converge, then you're fine. If one of them doesn't, or if neither of them do, it doesn't. Okay. So here's another p integral test, this time for the second type of, and here again, all right, this is the p integral over, say, 0 to a, okay? Now they enclose the 0 here, so you're including 0, which is what this one says, okay? But you've got your x in the denominator, and this is really improper because you can't evaluate that at 0. So it seems like to me this should be an open, a parenthesis there in front of the 0. Let's just see if they change that in the book. The p integral test here. Nope, they put it closed. Okay. All right. They weren't before, but it's fine. Because you just let it approach that. So if you do this one, do this integration for x p, x to the p. Before, if the p's were large and you're going to an infinity up here, then that converts. If p was 1 or less than 1, it can diverge. This is backwards from there, okay? Here, your problem is at 0, not at a, okay? And it's almost the same formula, okay? The only difference is you don't have the minus sign, so this stays 1 minus p. And this is good for all p's less than 1, okay? If p is equal to 1 or greater than 1, it diverges. So think of P being the power. Okay? They just call it the P test, P integral. It's a power integral. Okay? And if the power is less than 1, this will converge to that. If it's greater than 1 or even equal to 1, it diverges. So don't even mess with it. Okay? Now, this is going to try to tie the two of them together. I don't know if you'll find this instructive. Hopefully you will. All right. Here you have the case when you're going from some number, 1, say, or whatever number, to infinity. It's that first type of integration, okay? Where you have an infinite limit, okay? Obviously it's improper. If your P is greater than 1, you're going to be somewhere down here. This closes very rapidly here, so that will have a limit. If your P is, or your Q here is less than 1, okay, it's not, okay, because it's coming down slowly here. You're always going to have a finite amount that you're still going to. It's never going to converge. So this one diverges, that one converges. Same graphs though, x to the P, x to the 1 over x to the P, 1 over x to the Q. On this one, when you're going from 0 to 1, neither one of these are defined as 0. But if that P is greater than 1 here, look here. Even though it's closing in here, it's not closing in rapidly here. You have an infinite amount of area here. But it won't work if P is greater than 1.
It'll eventually touch 0 though.
It will, but it still is adding so much more. It's not going to convert. It just won't do it. This one, though, you see how it approaches it. This approaches 0 here too, but it's so slow. There's always some area there that you can't ever say, no, it's not going to matter anymore. Well, this one, that does it here. But on this way, it approaches it really quickly here. This one will converge here, but that one will not converge. So you just flip them around. If the P is greater than 0, this converges if you're going to infinity. If Q is less than, greater than 1, it converges. If Q is less than 1, or even equal to 1, it will not. Over here, if Q is less than 1, it will converge. Greater or equal to 1, it will not, because going this way, even though it approaches 0, the area is still empty. Okay. So that shows why the P test, they call them, the power test, they change directions if you're going the greater than some fixed number going to infinity, or approaching 0, where it's not defined. Okay. Now, there are other possibilities we have here. And I don't want to belabor this too long. I don't know if that reminds you of anything or not. What it reminds me of is Pool? A bull. Oh, okay. You're full of, never mind. Okay. All right. Yeah, I can see what you're saying there. It reminds me, thinking in terms of math, almost of a secant type function, right? Yeah, that's what you were thinking, wasn't it? Yeah, because at 1 here, going up and reaching vertical asymptotes there, it's not quite a secant function, but you know. But this is the infinite shaded area here does have a limit, okay? Now, that's not easy to tell looking at this, okay? Because this is a power of x squared to the 1/2 power, which would almost makes me think that's going to be at like 1 over x. It doesn't. It actually does have a limit there. But if we were integrating that, what would that be an integral on? What would you do to calculate that?
Trig thing.
Trig thing, okay. As in substitution? Yeah, which one?
Minus
Sine, exactly. All right. Such a positive
that's
confidence there. Yes, okay. Yeah, that would be a sine. And so that one happens to work. It's not a power function. So don't assume that just because it sort of looks like it might be, it's not. All right. Here again, it looks like they're going over some of the same stuff. There we go. Okay. All right. They're getting to a different thing now. These are comparison tests. E to the minus x, that does converge. We know it does. Okay. So from 1 to there, that converges. Okay, we did it earlier. 1 minus. Okay. Goes to 1. Okay. Here's another function, e to the x over x. Okay. Now, e to the x would be finite here too, because that's just a finite area. There's no limit, there's no ambiguity there. But this isn't happening there because you're dividing by x, so we're not even dealing with that to see if that's going to converge. But down here, because this crosses into us here, this function is always less than that one. This one converges, therefore this one has to converge. So if on an integral, all the values are always less than one that you know converges, then it's going to have to converge. On the other hand, if one is always greater than one that you know diverges, that's going to have to diverge. So those are some comparison tests that you can make, and that's what they're showing here. So I'm surprised they don't have a box for that. Yes, here's the comparison box. They did the illustration before they gave you the rules, which it may be the people who put the slides together just got them out of order. Here's comparison test. Assume that you have some function f of x is always greater than or equal to some other function g of x, and this g of x is always greater than or equal to 0. Okay? So in other words, it's almost like your sandwich theorem type thing. Okay? And this is good for any x greater than some value a, greater than or equal to a. If this one converges, maybe by the p-test or something else, that it converges, you know it converges. But you know this is greater than this one over that same interval from a, any x greater than a, then whether you know what this one does or not, if this is always greater than this one converges, this one's got to converge. It's got to converge. However, if the smaller function diverges from a to infinity, if that one diverges, then this one's got to diverge because this is always greater than or equal to that. So the area is going to be even greater. So that also diverges. The comparison test is also valid for improper integrals with infinite discontinuities at the endpoint. So if you were doing from 0 to a, but had a discontinuity at 0, then these same things work. Okay. So whether it has infinity at a limit or a discontinuity at a limit, if the one holds, the other does, and if the one doesn't hold, the other doesn't hold. Okay. I think this is another illustration of that type of thing, but I can't see it until it gets blown up here. All right. For instance, we did know that this one, 1 over the square root of x squared. That is, the p is less than 1. So from 0 to 1, that one converges for sure. Right? Well, this is even less than, for all values in here, it's less than it, so that one's got to converge as well. But this one diverges. That doesn't say beats about this one, because this is less than that, so it could still diverge. The divergence of the larger integral says nothing about the smaller integral. So just because that's diverging here, you can't say the smaller, it may be converging. But over here, yeah, this is less than this one, so if this one's converging, which we know it does, by the p-test, then this one has to converge as well. And it obviously does converge because it's finite, okay? Okay. And this is the last slide in this section that you're not responsible for. And these are your, basically a summary of your p-test. If p is less than 1, and this is going to infinity, p less than 1, this is going to infinity. This yeah. They've got it backwards, don't they? No, I'm sorry. That's the greater than sign. Why would really less than? If p is greater than 1, this one converges, that diverges. Because it doesn't approach 0 fast enough. Okay? And this one does approach 0 fast enough. If p is less than 1, this one diverges because it doesn't approach 0 fast enough, the value here, but this one, because on the upper end, that does converge. P is equal to 1, they both diverge. No ambiguity, they both diverge. All right, that's the section you weren't responsible for, okay. But if you ever run into them, hopefully that's enough that you can deal with it, okay. And now let's go to 7.7. And again, I'm not sure if you'll ever need these. But I'm not sure you won't need them either, because in the old days, engineers, mathematicians, scientists hardly ever dealt with probability. When I say scientists, what we call the hard sciences, chemistry and physics and things. You deal with formulas, you deal with equations, you don't deal with probabilities, okay? But once quantum mechanics came into play, now you're dealing with probabilities, and that's in chemistry and physics, and I mean, statistics is part of math too, so if you're heading that direction, you will have to deal with things, okay? Always the biological sciences and what you sometimes would call the soft sciences, the social sciences, they deal with probabilities all the time. So you would definitely need this. But I can't say that the hard sciences or engineering, you're not going to run into some probability issues. So if you do, this is what we're dealing with. Now I was an undergraduate physics major, and I did have one time the opportunity to take a statistics course. I had actually signed up for it, but then I got an opportunity to do a special problems class in physics, so I couldn't do both, or I didn't want to do both. It would be sort of an overload, so I dropped the statistics. I sort of felt good about that because the first day I went to that class, the instructor I thought was really flaky. But anyway, I'll just tell you why I said that. We had a chalkboard, and he said, up to now you've been dealing with calculus, and he wrote calculus on the board and misspelled it. Not good, you know. But now we're not going to deal with calculus, we're going to deal with statistics, you know. and he didn't really do much with it. All I remember of what he said, he misspelled calculus, so I was not impressed. Okay, but I had to drop the course anyway, so I never had it. But then in grad school, when I got into applied physics, in an area called soil physics and agronomy, we had to do biostatistics, okay? And the first course I had in that, even though I had buku math background, I found it just really an unpleasant course because it seemed so subjective, you know, and you had these various things and you just had to follow the formulas, and I never knew why we were following the formulas until I took the second course, and I thought it was going to be even worse. And that instructor, even though she was dealing with a bunch of ag majors, she said, well, most of you probably don't recognize this, but this is what we're talking about. And she drew the graph of the probability function. She said, we're doing the area under that. I went, why didn't he say that? You know, this makes perfect sense now, what they're talking about here. But they would just say a p-value, a k-value, this, that, and you just had to memorize a lot of stuff. I hate memorizing things. But as soon as she put it on the board as area under a curve, oh, okay, yeah, so this is the area, yeah, okay, this makes perfect sense. Of course, the other ag majors in the room, what he's talking about, yeah, anyway. So anyway, this is a probability distribution, okay? This is probably far closer to what most grade distributions are like. Y'all say you want to be graded, you don't say this, but yeah, a lot of times you do. Are you going to curve this? You're going to put it? Yeah. I told you before, a bell curve, you most of the time really don't want. Don't get it just right. Everybody sees a few B's and D's and the same numbers, by the way. Very few A's, but you'll get just as many F's. Usually you don't want that, you know, especially upper level courses. I've had some that professors actually did that, you know, they aggravated me like no end. Okay, but this is more normal, okay? If this is your distribution, then obviously your mean is not 50. The mean is over here somewhere. So you're above that, okay? So you 90 to 100, this would be your A's here, and that area is 15%. So 50% of the class is going to get an A. It's usually a lot better than a normal distribution, which would be like 1%. Getting A's or something like that. So this is what you're dealing with. And probability is dealing with areas under a curve. And you set a value and you see what's the area beyond that or behind that or whatever, okay? And figure out what that is, okay? That's, again, you're not responsible for this, but here's the one thing I want to say about this probability curve, P of X. The total area under here is always 1, okay? Because the probability that you got some score is 1. I mean, everybody gets a score, okay? So everything's covered. From 90 to 100, probability that you're in the percent that there is 15%. It could not ever be more than 100%, right? You know, if you only have 7 people in the class, you can't have 8 A's, you know, so anything like this. It's always going to be something less than 1.
I had a friend, she took organic chem.
Yeah.
And then she made 100 on the test. The professor got mad, so she got 100 because he doesn't like people making 100s on his exams. So he made the next test harder, just because she got 100.
And what's wrong with that? No, I'm just kidding.
I mean, she still passed the class with an A because she's like very dedicated, but it's kind of crazy how a professor would like make it harder just because one student made 100.
This is actually almost a step further. When my wife was at grad school at UAB in the School of Public Health, she was taking a course from her advisor, and she had made all A's up to that point. And he gave her and this other woman in the class B's because he said nobody's perfect. So even though her scores, she could have argued, should have been an A, he still said no one's perfect, so you get a B. And if
I
you're
don't
giving
gotta
him,
worry about that.
huh?
I don't gotta worry about that.
Oh, okay. All right. Good. Okay. So I thought that was
Okay
the
with B. Let's do it for 3.0.
yeah.
Hey,
Well,
give me a few.
I know.
my older brother in some courses all he wanted was a C, and he was happy with that. All right. Now, oops. This is what we were just talking about, the probability from minus infinity to positive infinity. What's the probability that something exists is 1, okay? Has all the values in there, it's going to be 1. Anything less than negative infinity, and anything greater than negative infinity, less than positive infinity, there is a very small chance you could be beyond something. So, but this is the infinity there, and you already picked that up on that. All right, now here's something a lot more normal that we look at. Though this is quite a normal. This is probability density function, just one of them. And here we're interested in what's the probability with this density function that the values will be between 1 and 4. Okay? Well, if you could integrate this, that would be okay to do. No, and perhaps you could. But on the other hand, if you just knew what they were, say from 0 here, that would be 50%. If you could figure what they were from 4 to infinity, subtract that off, subtract off 0 to 1, then that's another way to get there. So quite often, if you can integrate it, yeah, integrate it from 1 to 4, that's fine. You get the answer. But sometimes you can't, but you do know other things about it, and you can derive it sort of indirectly. Okay, and that's a lot of how statistics works. You know, you don't know exactly, but you can derive things about it. Okay, and that was actually an example. So if you want to go and do that, you certainly can. That one is integrable, by the way, by an inverse tangent, you know, type thing. Okay, or a tangent thingy, I think it's sometimes called. Okay. Also in probability, we sometimes talk about the mean, and we also will sometimes talk about the sample mean. This, I think, is the true mean, and that would be, it's a weird formula, but that's what it is. It's the x times the probability of x. It goes from minus infinity to infinity. The mean or the average value of a random variable is this quantity here. Okay? That's an average value. Now, I don't know if you remember the mean value theorem that we did in calculus, or what was that, Cal 1 maybe? Yeah, it seems like maybe you did, or maybe we're going to hit it later in this, I don't know. But, or maybe it was earlier in this term. But, you know, you took, if you had a function here, whatever it was, the mean value, yeah, you did the area under there, and what would give you that area, and that would be, this is kind of like that. Not quite the same, but somewhat similar. And that would be your mean or your average value. Now, another term they use a lot would be this one. This is a probability density. You have a bunch of them. This is the exponential probability density. Okay? And I don't know if you are at all familiar to compound interest and constantly compounded, you have continual interest? This reminds me of that formula, okay, of continuously compounded, not annually or semi-annually or monthly or daily or something. This is a continuous compounding. That looks like this one, and it's sort of, that's an exponential probability density. And I don't think it's an accident, they are somewhat similar. Okay. Again, this is just a slideshow. Hopefully it's making just enough sense that maybe you can figure out what to do with it. If you were hired as a consultant for a company and you're trying to estimate when you should have the action staffing or other things like this, you might be interested in something like this. The customer arrivals, this shows an exponential distribution. You have some constant there that's R with 60, and it doesn't seem very realistic because you have most of your arrivals at 0, but they're dropping off later. So again, if that fits your problem, use it. So that's an example of the mean of an exponential density function. Okay? Here is our good old favorite. This is the normal distribution function. Okay? Weird coefficient here, 1 over the square root of 2 pi. And pi is inside the radical there to the integral of that. What this is doing is making sure this has a total area of 1. If you didn't have that in there, that wouldn't have an area of 1. With that in there, it does. And you might say, where does the pi come from? There's no circle, there's no trig function, there's no anything. And you're right. Pi is one of those special numbers that you can't live without. Okay, irrational, but it just shows up in all kinds of things, not just trigonometric things or circular things. But this is your probability density that will give you normal distribution. Okay? And the normal distribution is your good old bell-type curve. Okay? Now, the previous one was centered at 0, and it was a bell distribution centered at 0. This is one centered somewhere else, centered at mu. Okay? So that's one difference to it. Okay? The other is, this isn't just any old distribution. This is one that has a standard deviation of sigma. And that's what the sigma is. Mu is the mean, sigma is the standard deviation. Mu, mean, m, that's the lowercase m in the Greek alphabet, the mean, okay, lowercase s in the Greek alphabet for standard deviation, sigma. Okay, so this would give you something that looks like that bell-type curve, and it is a bell curve, but depending on the size of this, the mu shifts it off of 0 wherever that mu is, okay, but the sigma changes the thickness of it. The normal distribution curve may be like this, with a larger sigma, it may spread out some. With a very small sigma, it may go very narrow, okay, and that's will give you also normal distributions, but with certain means and standard deviations. Okay. Here's an example of what I was just trying to talk about. This is not with a change of mu's, but with change of s. Oh, yeah. These three are all, the mu's are 0. The mean is 0. You have just as many likely to be positive as negative, okay? This was a standard deviation of 1. That's your standard normal distribution curve, okay? This was the standard deviation of 2 that broadens it out, which also lowers the mean here. And this is a standard distribution of 0.5, narrowing it down. So now it's a very narrow curve with a much higher mean, okay, or probability of being on that mean. This is one that you have the standard deviation of 0.75, a little higher than the normal, but not as high as 0.5 in between those two, but the mean is shifted from 0 to 3. Okay. So that gives you this. Now that's more characteristic of what you'll find in real life data. Okay. Most of the time your mean isn't going to be 0. I mean, you would think if you're measuring something, it usually has a mean value. So it has a value somewhere out there. But it still has a standard deviation. So this allows you to have that kind of distribution. Okay. Now, this is when you're integrating that normal distribution, okay? You're getting the probability that your value is going to be less than or equal to z, okay? See, this will give you all the probabilities from negative infinity up to z, stop there. That would be the area under that curve would be, that this is your normal distribution thing, up to z. Now the z may be over here, it may be a negative z. Yeah, it could be anywhere there. That would give you the area of everything up to and total area would be 1, of course, so this will be something less than 1. So here would be the picture of what we were just talking about. Here's your normal distribution curve, okay? They don't have any labels on it, but that's about how it looks. And the area from that we were talking about before, from negative infinity to z, if z is positive, would be here. That area would be this one. Something less than 1, because the area under the whole thing is 1. So this would be something greater than 0.5 too. Up here would be 0.5, guaranteed, because you're centered at 0. So this would be something greater than 0.5. I would guess that's probably 0.85 or something like that. So that's your area under that shaded region. The likelihood that you're less than or equal to z. All right. All right, here's the deal. If x has a normal distribution with a mean mu, which may be other than 0, and a standard deviation sigma, which may be different from 1, or could be 1, then for all a's less than or equal to b, the probability that the expected value here is less than b, less than or equal to b. So you're somewhere within that, then that would be f of b minus mu over sigma. Whatever that area under the curve evaluated at that value. Now, if you were looking for the probability you're between, your expected values between a and b, then you would do it for b, that's the greater one, minus for a. So in other words, you subtract off, this is the probability up to b, and here's the probability to a, subtract that off, and that gives you the stuff between a and b, wherever that is in the function. And that gives you that, because this is the probability of anything from negative infinity up to b, and b is greater than a. So then this one would be the probability of anything up to a, subtract that off, and you get the difference between a and b. So that would be the probability that you're whatever your value you're looking for is between A and B. And that would be this kind of a picture. Okay? If this is your A, that should be, here's your normal distribution curve, here's your mu, we're assuming it's slightly positive. Okay? This shows A greater than mu, fine, no problem. The F of the B part would be all the area up to B minus all the area up to A, that leaves you just the area between A and B.
What about the area after B? Well, I guess.
Yeah, that would be 1 minus this one. Because the whole thing is 1, so the area over here is 1 minus this area, and this is the area over here, so you're between A and B.
So this is pretty much back to what we did a long time ago, like finding the area.
Yeah, I mean, that's actually what the statistics do for you. They usually have it in tables, so you don't actually have to do the, I don't want to do that integration. It's really messy. In fact, I'm not even sure that's doable. So, but they have all these calculated, the tables are all done for you. And that's what it's representing there. All right, enough of that. That ends that one. Those two you're not responsible for, but hopefully it was just enough that if you ever need it, you can go back, look it up, and hopefully have at least a little bit of a feel for what's going on there. I don't know if that was accomplished or not. Okay? If not, sorry. Okay. Sorry I wasted your time. But let's do section 7.9, numerical integration. Almost looks like, look at this. Wait, we were just doing that. It's not quite the same thing, but close. Let's blow that up. Boom, I blew it up. Okay. Now, that looks really familiar, doesn't it? An e to the minus x squared over 2. Okay. Now this isn't a probability function, but it's a lot like one. The reason I say that, this value here is 1, and the probability thing, the whole area under here is 1. So that can't be, but it's very similar to it. But that's an integration, just like the other one I said. You can't do it. You cannot. We don't have the tools for doing that. We don't have the thing. So how do we do things like this? Numerical integration. And that's why they have the tables and stuff like that, because it's done numerically. The area under the bell-shaped curve, which you could think of, it's not a probability because it's greater than 1, but it would be a bell-shaped curve, computed using numerical integration. Okay? And this is going back. You were mentioning going back like you used to do. This is almost going back to what you originally did with Riemann subs. Remember when you were first learning integration? We're almost going back to something like that. You're going to determine the area here by breaking this into little segments and taking values here. You can calculate the value of any x value here. You just can't integrate the value there. You can calculate the value. So you calculate the values and you approximate using rectangles, trapezoids, or other things, and then you go from there. And the smaller you get your increment sizes, the closer you are to getting the actual numerical value. Okay? That's the rule. Okay? Now, all right. Now what they've left off here is the wording here. To approximate a definite integral from a to b, definite integral from a to b of f of x dx, but we can't integrate it. I mean, the f of x is really complicated. We don't have any tables in the book. We don't have any rules. We don't have anything to actually integrate it. We fix a whole number in. You choose an in. Okay? How many intervals do you want to have? That's what the in is. Second? 6. Okay, that would be a fine in to do. I would usually use the power of 2, but 6 is fine too. There's nothing wrong with 6. So then your first interval is going to be where A. You're not interested for things less than A. You're not interested for things greater than B. You're only interested from A to B. So have your x of 0 at A and your x of n at B. Okay? You got n. Generally, we use them equal intervals, right? Why not? Okay? Equal intervals from A to B. Well, that tells you what your increment size is. Your increment size would be B minus A divided by n, right? The length between A to B is B minus A. Divide that by n, that's your delta x. So the delta x is B minus A divided by n. So your x of 0 is at A. Your x of 1 would then be at A plus 1 increment. And the delta x is B minus A over n. And then your x of 2 would be A plus 2 delta x's. It would be here, okay? And then x of 3 would be here, and 4, and up to 6, you would get up here, okay? So then you would have a value at each of those, an x value there. X of 0 is A, x of 1 would be 1 increment past A, x of 2 would be 2 increments past A, x of 3 is up that, and then finally when you get to x of 6, you're at B. Okay, so you split that into 6 equal increment size. Okay, now, next thing you do is calculate the value of the function. Okay, like I said, the function may not be integrable. You can't find it in a table or anywhere else, but you know what the function is. You can plug in a number, get an answer. Okay, so you plug in x equals A, plug in x equals A plus delta x. So your y sub j, your j values for each of those ones that you plug in, is going to be alpha of x of j, whatever the x of j is. X of 0 would be A, whatever. So that would be alpha of A plus j delta x. And remember, your delta x is B minus A over n, and you're doing the jth increment of that. So that's going to be your alpha that you evaluate there. So basically, that gives you how the height of that curve there, right? Okay? And you're trying to get the area here. So you have a delta x is your width, and the height is the L value. Okay?
So what's the J?
J is just a counter. Okay? So J is 0 at A, at 1 past A, 2 here, 3 here, 4 here, 5 here, 6 here, B. So J is just whichever one, which increment you're at. Okay. All right. Shouldn't end the phrase with a preposition, but I just did. Okay. This is an English class, is it? Okay. So sorry it's not. Sorry. All right. So here's what we would have. Now this is a rule, and sorry about this. Your book hits the midpoint rule first. The slideshow is doing the trapezoid rule first. So I can either, you want me to stay with the book or stay with the slides? Okay, let's, what's that?
It has both of them next to each other.
Yeah. Where are you looking at? Bottom page,
431.
no, those are midpoint, both of those midpoints. Your trapezoid is over on 422, or 32, sorry. Okay, let me turn over and do trapezoid first, midpoint first. I'll get the midpoint. here we go. I can't read that. Which is this one? That's a problem. I think that's still trapezoids, I think. Yeah. So here's where we start with midpoint. And then remind me to go back and pick up trapezoid. I'll say, where's trapezoid? Okay. Okay. Here's the midpoint rule. Now they start with the rule. They haven't shown you the pictures yet. So let's see if I can find some pictures first. Ah, here's the picture. I'll try to do it the same order the book has. Okay. This is the midpoint rule. Now what we've done, we've split the interval from A to B into n seconds. 6 will be fine. With the midpoint rule, the n has to be even. Has to be, so 6 is still okay. In the trapezoid rule, it could be anything. But in the, I think I'm saying that right. No. Either one of them can be it. 6 is still good. So they only show 1, 2, 3, 4, 5. So the obviously 5 is fine. So if this is your curve and you're approximating the curve using the midpoint of the rectangles between A, x of 1, x of 2, x of 3, x of 4, x of 5. You had 6. Yeah, just throw them a little bit. We're going to estimate at the midpoint of every one of these. That's going to be the y value we do. So the area under this that we're using as an estimate overestimates this part but underestimates this part. Okay? So averages out not bad. It underestimates here, overestimates there. Underestimates here, overestimates there. That was really close. Underestimates here, overestimates there. Underestimates here, and really pretty seriously underestimates there. Okay? Now, if you think about this though, if you use the midpoint here and drew a tangent line there and then extended these up, that's what the midpoint rule is actually giving you, is the slope of the tangent line here. Then you have exactly a much better estimate here. This one overestimates over, under, okay? That's also the midpoint. The ounce of n is the sum of the areas under the midpoint rectangles, but it's also the sum of the areas of the tangential trapezoids. So it is a trapezoid, but it's not the trapezoid rule. It's still the midpoint rule. In here, okay? But it's using the areas of the tangential trapezoids, not the trapezoids we'll be doing later. And this is why the midpoint is actually better than the trapezoid. Okay? But you calculate the value at the midpoints. Here, you calculate the value at the midpoint, but then you draw a tangent line to it. And this, you see, this was a little bit bigger area here, so that's an overestimate. This was a bigger area than there, so that's an overestimate. This is awfully close to being equal, and I can't tell if it's over or under. Awfully close to equal. This was underestimate was greater than over, and that's why the trapezoid is underestimated here. And here, because this was a bigger area than this, it's slightly underestimated there too. Okay. So that sort of ties it together. That's the midpoint rule. Now they haven't given you the formulas for it. They have, but we're not in the text yet. Okay. So let's get them in the text, and that's back here. Here is the midpoint rule. what we do to estimate these values. All right. The nth midpoint approximation to that function there, okay, you use 6, they were using 5, whatever it is, midpoint for n equals whatever number it would be. The delta x, remember delta x is b minus a over n. Always, okay, equal intervals here. That delta x, so every one of these is going to have a thickness of delta x, right? So that's going to be the width, and the height is going to be the length. Here's the height, F of C1. Now this C1 is not any of those J delta X's there. This is the midpoint between each of those. So you do the J minus 1/2 delta X. The C sub J is not at this end or that end, it's at halfway in between. So it's A plus halfway between the J between the next delta X. Yeah, so it's J delta X would be the one at that end, and halfway to get to delta X gets you half the way up there. So these are your C1s. Now they're not nearly as complicated as this makes it seem. Okay.
So like,
What's that?
in that you would find the integral of the f of x, and then for each c.
Yeah, and then
you would
you go
just
halfway
plug
in between. Yeah.
Just plug in.
Yeah. Right. And that's what you plug in. When we do one, you'll see it really makes pretty good
Yeah, I'm
sense.
pretty sure we did this last
Oh, really?
one. Yeah.
Huh. That's surprising.
Yeah, we were
Because
going back, like towards the end, it was just like too much. Like, I think she was trying to cram stuff in.
yeah.
I feel like I've done this before.
You what?
I think I've done this.
Oh, okay. Did you have any Cal in high school? No. Okay. All right. So I'm trying to keep up with. All right. Here's the next slide here. All right. Here's a rectangle, and you can think of it. This is what I was trying to wave my arms to do. The midpoint here, here's the. Okay. Here's the midpoint value for x. You calculate the value on the curve at that midpoint. And you can either think of that as that rectangle there, which over and under some underestimates here, overestimates there. Or you can think of this as drawing the tangent line of that rectangle at that point, and then you get this value and that value are exactly the same size, so that gives you the same. The trapezoid down there is exactly the same here, and that's actually, as you see when we do the trapezoid rule, it's a better trapezoid than the one they use. Okay, one they use is this one to that one, and that's just not as good a trapezoid as this one would be tangential at the midpoint. Okay, but the rectangle and the trapezoid have the same areas. Much easier. Well, I was going to say easier to calculate the rectangle. You just this times that. I mean, that's all there is. But actually, when we do the next thing we do after we do the trapezoid rule, then we actually are going to be using these values. Okay. We'll see. We'll get that in a bit. All right. A lot of blah, blah, blah before we ever hit our first example here. Okay. That's the slide we've already looked at. Okay. Now this is going back to the error bound for trapezoid and midpoint, since we aren't there yet. We haven't done trapezoid rule. So we just did all that blah, blah, blah on midpoint rule, but didn't do a single example with it. Now we're going back and do the trapezoid rule, not the tangential trapezoid like we just did, but we're going to do the one. Goodness gracious, where is it? All right, here we go. I can't read that. Oh no, we already did that one. All right. Here is the trapezoid rule. As opposed to the midpoint rule and the tangential trapezoid. That's not what we're talking about here. On the trapezoid rule, we break up our intervals just like we did before. 1, 2, 3, 4, 5. So you can have odd numbers here. That's perfectly okay. And you do A sub 0. A is your x of 0, B is your x of n. And then you have your x of 1, x2, x3, x4 in there. Now what you do here, you do the area of the trapezoid formed from y of 0 and y of 1. Okay? You don't have to measure the center. The center point, that is not really what you call it. The midpoint, okay. Instead of the half, okay. Midpoint. They name it C, and that's why I think of it as the center. But the midpoint, you don't have to do that. You just use these values you already got. Do your y, each of the x values. You don't have to do halfway in between. Just do the y's there. And then the area of the trapezoid, by the way, is this one plus that one divided by 2 times that. Okay? So that would be basically the difference between these two, midpoint of that. That would be the rectangle that would be there. That would be the same area of this one. Not the area at the center point, at the midpoint, but the area here. It's y0 plus y1 divided by 2 times that. That is your trapezoid, the approximate area under the graph. Now, again, this one's totally underestimating, very close to right on the money, overestimating there and overestimating there. Okay? So that's basically what you're doing with the trapezoid rule. And we've just run out of time, haven't we? Okay. Where are we here? Where are we, Waldo? Okay. We're going to do, the next thing we do is this slide right here, figure 5. Okay. I don't think we got enough to do any homework problems, so I guess that means y'all don't have a test in hand, do you?
I still have.
You have yours, okay. Sorry, nothing I can give you extra. Work on your paper here. Okay.
I did one. Can I show you one of my problems I worked out?
Yeah.
And then tell me if it's right or wrong.
Or I can just laugh out loud.
Yeah.
Okay, that's good. Okay. All right.